Fusion, the international science radio show.
Richard Garner is Associate Professor at Macquarie University in the School of Mathematical and Physical Sciences. He gave a talk at the Frontiers of Science Forum this year on games for computing and computing for games, on pure mathematics and its applications. Hello, Richard.
Hello. Hi,
Hi, how are you?
I'm good, thanks. How are you?
I'm good, thank you.
So, my name is Richard Garner. I'm Associate Professor in Mathematics at Macquarie University, Sydney, and I work in an area called category theory, which I hope to tell you a bit about.
Fantastic. So I guess the first question is, what is category theory?
So, category theory is a part of pure mathematics. So it's on the more abstract end of pure maths. And so what it's about is finding patterns and structures which reoccur across different areas of science. So that might be within maths itself, or it might be in related areas. So things like physics or computing, or sometimes biology and things like this. And so the idea is you find different patterns that turn up in different places. Okay, so there might be some construction in physics which resembles some construction you do over here in maths. And you say, well, what's the common pattern behind these? And is there some sort of language or structure I can use to unite them? And so category theory is about finding those languages and those structures. And so basically providing tools to workers in these different areas to, one, simplify their problems, and two, maybe find new ways of talking to each other about them.
Right, that sounds absolutely essential. Look, I can vaguely remember from my physics degree a long time ago that one of the things they were teaching physicists was to look at the physical problems and try and turn it into a mathematical problem that they would recognize of a type that they might have already learned to solve. And
Yes.
so this sounds very closely related to what you're trying to provide the tools for them to be
Yes.
able to do that sort of thing, and for all other types of disciplines as well.
That's right. So that's exactly correct. So it's kind of like this. So when you do math, you take something from reality and you abstract away from it. Okay. So as you were saying, in physics, you might turn a physical problem into something involving some kind of mathematics that you already know or understand, and then you just go away and you solve the mathematics. And so in general, the advantage of doing this is that, one, you can then generalize the mathematics beyond the sort of situation that inspired it. And so that can be useful because sometimes it's like, okay, so maybe you understand how something works in like 2 dimensions or in 3 dimensions because you can visualize it. But then suppose you're doing like special relativity or something, right? So then you have to think about space-time rather than just space. And so then space and time are all mixed up in this complicated way, but the maths stays kind of the same. You can use the same maths to understand it. And so this stuff, which was very intuitive in 2 or 3 dimensions, is no longer intuitive kind of to your brain in 4 dimensions unless you've turned it into this maths beforehand. And so in a sense, you're using the abstraction to take the complicated thing and turn it into something that you can kind of think of independently of the complicated thing, and then try and reapply it back to whatever your real world problem was. And so that's exactly what you're doing in category theory. So I guess the fundamental difference is that it sort of happens one step further back. So you can sort of imagine that if you're a mathematician or a physicist, after a while, these abstractions you've created of reality take on a reality of their own. And so in a sense, in category theory, what you're doing is you're taking those sort of interior realities that have come from this process of abstraction, so the stuff that the physicists are dealing with. So maybe after a while, you're like, okay, I understand space-time now, and it has some kind of reality to me. But then at that point, there's things you're like, whoa, now this is going beyond my intuition because it's something else that I don't quite understand. And so then category theory is sort of the one step back from that, which is to say, okay, let's take these already kind of abstractions of reality, and then let's try and understand those from a sort of common perspective. So that makes it sound incredibly abstract, right? But actually, it's not as bad as that. So, I mean, there are kind of very direct sort of real world applications of category theory as well.
So it sounds like it's helping people think about things that they're less familiar with, particularly if they're doing research at the cutting edge, or they're just, even if they're learning things that already exist or already known about,
Mhm.
that they can get a better handle on it intellectually.
Yes. So it's kind of like when there's a problem, that problem can have two aspects. One can be that it's genuinely sort of something new and hard and difficult. And then there can be another aspect of it, which is just that actually it's just that you're expressing it in the wrong way that makes it look complicated. So, I mean, people, I mean, there's kind of, I suppose, what is really, I mean, it's sort of a bit of a cliche, right? But people say that, like, if you're a philosopher, then you have to speak German because when you speak German, it has all these sort of phrases and terms that make it really good for describing philosophical ideas. And if you're going to write kind of beautiful expressionist poetry, then you should do it in French or something like that. And so it's the same kind of thing. It's like the language you use directly influences the way you can think about something. And so category theory is about trying to find a better language for expressing certain ideas that kind of takes away some of the complexity, which is there for kind of the wrong reason, and then just leaves you with the bit that's hard because it's genuinely hard. And then you can try and work on that unimpeded.
And it's interesting that you talked about people's intuitions, because
Mhm.
people outside mathematics don't often associate that with mathematics.
That's right. I guess mathematics is kind of like that. It's I mean, I think a lot of people have the have a certain view of what maths is about, and that diverges kind of radically from what kind of working mathematicians think mathematics is about. And a lot of the time it is about trying to take some intuition or feeling for the way that something's supposed to work and then crystallize that into something quite precise and formal. So I mean, again, it's I guess a good analogy is, I mean, it's sort of a stupid analogy maybe, but it's quite I think it's quite a telling one. So it's like you think of, I don't know, so you think of chess. Okay, so chess is a game, and at some level, it's an attempt to formalize kind of some ideas of strategy and how you can kind of do certain effective moves in, I mean, I guess originally it comes from actual warfare or something like that, right? And the point is that even though it's a gross kind of simplification and abstraction of that idea, nonetheless, within there, you can develop these very elaborate strategies for playing this game.
Mm.
And in a sense, you do that in maths. You're going to try and come up with a very simple set of rules which are highly productive in the sense that you can get all sorts of complicated things out of them. And in particular, you hope that those complicated things somehow map back onto reality in some way.
That would be useful.
That's right. But I mean, there's more to it. I mean, when I say that, I'm saying something about mathematicians, which is that it would be useful if it mapped back onto reality, but it's not a prerequisite, right? And often this is what happens. You do stuff just because you're like, oh, this seems kind of pretty and interesting. And again, you have these intuitions as a mathematician, like inside your head, you're like, okay, I have a feeling for what this is because I've spent a long time thinking about it. Um, and so you do this just because you're like, well, this seems kind of, there's an intuition there and it seems kind of pretty to me. And then after a while, it turns out that it's actually useful. And it could be that the while is quite a long while. So, I mean, group theory was invented at the end of the 19th century, I guess, and it turned out somewhat later to have lots of applications in physics. And so people didn't really expect this necessarily, but it turned out to be the case.
And that was also the case with Boolean algebra, wasn't it? It was invented quite some time ago.
That's right. So I guess that was invented by George Boole, indeed, who was a reverend, and I'm not quite sure why he came up with it. He just sort of, I think he sort of thought it was a fun thing to do. And as you say, like, and then much later it turned out to be the things that you need to describe what's going on in computing, I guess. It's the sort of basic structure right there.
Yes.
Yeah.
And so, do games have something to do with this mathematical intuition?
So there are lots of ways you can come at this, I guess. So I mean, you start from the idea of a real world game, okay? And so, I mean, there are lots of different kinds of games. And I guess the sort of games which are relevant for mathematics are kind of rather boring two-player games where people make one move and then they wait around until their opponent's ready to make their move, and then it kind of carries on like this. Now, of course, games have a lot more than that, and there are a lot more things that one could do in a game. But from a mathematical perspective, you abstract away from that and you just keep this structure here. So these kinds of games have been used all across the mathematics. So I mean, I guess sort of famously there's the sort of games that turn up in economics, right? So John Nash has these famous games and things like the prisoner's dilemma and things like this. And so that's the kind of game where there's a sort of um, a reward aspect to it. It's right, okay, if I make this move, then I'm going to win this much money. And if I make this move, I'm probably going to completely wipe myself out and things like this. Okay, so in maths, the kind of games that are relevant are a bit simpler than that. It's basically just win-lose. Okay, and so the reason is it's related to what you're saying. It's like to do with you're sort of interested in things like Boolean logic, where things are either true or false. And so it's like, okay, I want to use games to sort of represent. In fact, you're going to be doing logic with these games. So you're going to be taking your intuitions about logic and you're going to be using games to sort of represent facts you might try and prove or disprove. So that's, I guess, the intuition comes from real world games. And then it's like, how can I use this to describe certain things that arise within mathematics? Does that make sense?
Yes, I think so. So you're talking about games that not only you use your intuition from the real world to find out new mathematical truths.
Mm-hmm.
Is that right?
So, so let me see if I can explain what the idea is. So, um, so let's give a sort of fairly concrete example of this. So imagine we've got a computer and we've got some programming language which we use to program the computer. Okay, so normally if you've got a programming language, somewhere there's a big manual or like a specification created by an international body, and that will tell you what the programming language is supposed to do in response to certain commands. Okay, and so these documents are like 800 pages long or something like that. And if you actually go out and you check, so that there are like compilers out there that are supposed to take this programming language and turn it into something the computer can run. And if you check that most of those compilers don't really actually implement what the language is supposed to do precisely, but it's kind of close enough that most of the time it works okay. Okay, so, and what this is going to do is introduce all sorts of little problems in terms of, okay, if I write this program, I'm not quite sure what's going to happen necessarily when I run it. Okay, and so that is the problem of programming language semantics. So the semantics is what does the computer actually do in response to the syntax, the program that you put into it. And so in mathematics, what you want to do is somehow model the programming language in a way that you can understand from a mathematician's perspective, maybe in terms of something like a game, exactly what's going to happen in response to the various commands that your language has. Okay?
Yeah.
All right. And so the idea is that you're going to kind of set up various sort of two-player games that are well adapted to certain kinds of program that you might try and write within a computer. Okay? So you might imagine I'm going to look at programs maybe that they're going to take a true or false value and two numbers, and then depending on whether the input was true or false, they're going to do something with those two numbers and return another number. Okay? So that's a sort of specification for a kind of program you might have. Okay, so it's a program that maybe takes, if you wrote it out, it would be like, okay, I've got a function called Derek or something like that. And my function Derek takes as input a true or false value, which I'll call X, and then two numbers, which I call number one and number two. And then my program can do various things using this true or false value X and this number one and number two, and then they can return some new number, okay? So maybe my program would be something like this. If my first value, my true or false value is true, I'm going to add the two numbers up and return that. If my true or false value is false, then I'm going to multiply my two numbers together and return that. Okay? So that's a kind of little program that you could write. Does that make sense? So my program takes a true or false and two numbers as input, returns a number as output, which is either going to be their sum or their product, depending on whether I said true or false with that input. So the idea now is that you're going to create a certain two-player game out of this sort of situation. And so this is going to be a two-player game in which one of the players is the computer and the other player is the environment. Okay, and so what does the environment do? The environment's the thing that's going to kind of give you your input to your function. Okay, so the environment is going to come along and it's going to kind of produce for you, it's going to say, oh, I want to say true 10, 55 or something like that. Okay, so the environment has that information, like what are the inputs to your program going to be? And so then your computer has to go away and do something with those inputs and produce an output. Okay, and you can set all of this up as a certain game where the players take turn asking each other's questions. So in this sort of game, the computer would start off by asking the player, what's your X? Is it true or false? And then the computer would ask the environment this, and then the environment would say, oh, my X is true. And then the computer would say, okay, well, what's your first number? And the environment would say, oh, my first number is 10. And then the computer would say, okay, what's your second number? And the environment would say, my second number is 77. And then the computer would say, oh, in that case, I'm going to give you 10 plus 77, so that's 87. And then the computer's won because it's managed to successfully output a number in response to the information that the environment has given it. Okay?
Yep.
And so the idea is that this same game, there's lots of ways of playing it. And those can correspond to all the different things the computer can do in response to the inputs it's given. So you can imagine that if you changed your program, then maybe when I put in true, it's going to take the first number and square it and return that. And when I put in false, it's going to just return 0, no matter what else happens. Okay, so that's another valid thing that my computer could do. And that corresponds to playing the same game, but using a different strategy to play it. Okay, so you're going to ask different questions, and then the response you give to those questions is going to be different. Okay, but still in the end, you're going to win the game because you always win the game by giving a number at the end. Okay, by returning a number at the final step. So, I mean, you could decide you're going to lose the game by refusing to answer and say what number you're thinking of. And in that case, it's like, okay, so that's not a successful sort of way of implementing this program which takes these inputs and returns this kind of output. Okay, so that was a kind of, I guess, a very long explanation of how this sort of works. And I suppose maybe the key points really to take away there are that you start with some kind of specification for a computer program, and then you turn that into a certain kind of game, two-player game, such that the ways in which you can win the game as the computer correspond to the different programs that you can write, which sort of implement that specification. Okay, does that make sense?
Yes. Yes, I think it does. And so the computer would lose if it turns out that the programming language didn't quite match what it was meant to do in the specifications.
So okay, you could try writing, that's right. So you could write something which is sort of an ill-formed program or something like that tried to do something super weird. And in that case, you might come up with something that's not a winning way of playing this game. And in that case, you've failed to implement successfully the correct specification that the program is supposed to have. So maybe it's less that you write something that's sort of complete nonsense. Maybe it's more that you write something that kind of works but doesn't implement the specification it's supposed to do. Okay, so instead, rather than returning a number at the end, it just stops and just refuses to return a number or something like that.
So could that sort of game reveal a problem with the implementation of some specifications for a language?
So the objective would be, so there are various things you could do here. So yes, one is you could try and check if the implementation of a language was correct. Another is if you were satisfied that your language was correctly implemented, then you could do something subtly different, which is to verify that the program you've written is the program that you want. Okay? So the thing is, right, suppose I've got a program that all I know in the computer is that it takes two numbers and returns another number. Okay? And the specification you were given by your client is that they want a program that will add two numbers together. And the program you give to them is a program that takes your two numbers and multiplies them together. Okay, so you failed to implement the specification, I hope. Did I say two different things there?
You did. I think you did. I'm not sure
Okay, good. Yeah.
now whether I
All right.
perceived it wrong.
Yeah. Okay, good. So in that case, you've got a completely valid program, right? But it hasn't fulfilled the client's requirements.
Yep.
And so in that case, it's sort of trivial what the problem is. But in more complicated cases, the specification might be like, okay, I want a program which will securely transfer information between this bank server and this ATM or something like that. Okay, and in that case, it's more complicated. There are more ways you could go wrong, and it's really bad if it does go wrong.
Absolutely.
So in that circumstance, even though there's a program which is kind of correct in the sense the computer doesn't kind of just not produce answers or anything like that, it can still be wrong in the sense that it fails to implement kind of the specification you have from your client, basically. Okay. So how does this stuff I've just been talking about help in this situation? So imagine you've got this perfect mathematical model of how your programs can be represented using these games. So those games are things you can reason with mathematically, okay? And so in particular, you can make a mathematical statement that says, I expect when I run this game with inputs like I and j, then it should return I plus j, okay? And so then you can take your description of your program, which is now as a sort of strategy for this game, and you can go away and you can do some mathematics and check that actually it is going to always give you the right answer when you give it these inputs, okay? So in a sense, this is a bit like what we were saying earlier. Like if I've got a real world problem, like from physics or something, then I create some mathematics which represents that. And then I go away and fiddle around with the mathematics and then map that back onto the real world. So it's the same here. I've got my computer program. I create a mathematical representation of it, say using games. So that's just one approach. There are many approaches, but let's say using games. And then I reason mathematically about this game. And then hopefully I conclude that this mathematical representation of my program does the things I want it to do under all circumstances. Okay. So this is, I guess, what's called program verification. And there are various ways of doing this, depending on how you map the computer program into kind of the world of maths. So there are various other formulations you could use, but this is one formulation. And so, I mean, there's a bit of a gap, right? Because real world programming languages are super complicated. And you start from these sort of things maybe that you can represent by games, and they're sort of fairly simple programming languages. And so you sort of got to move a bit towards the middle somehow. You have to kind of take your theory, which starts over here, and your practice, which is very complicated over here. And hopefully you can sort of marry them in the middle. So you have some language in the middle, which is kind of expressive enough you can actually program in it, and also simple enough that you can reason mathematically about it completely correctly.
Wow, that sounds very important with, well, as you say, not just from programming languages, but any sort of thing, to be able to verify that it
That's right.
makes sense.
That's right. So, I mean, Australia actually has quite good form in this area. So there's a group who were at CSIRO called Data61, CSIRO Data61. So Data61 still exists at CSIRO, but there was a group there called Trustworthy Systems who have this verified, completely verified kernel, so just the core code for embedded systems. So embedded systems are things like the processors inside your phone, or maybe inside an ATM, or some, I don't know, like the autopilot on a plane or something like that. Okay. And so they have a completely verified core code for one of those. And verified means in this case that it's kind of proven to do exactly what it's supposed to do under all circumstances. And so that's really, really important because basically this is the very core of your computer. And if that doesn't work the way it's supposed to, then you can't trust anything that you kind of do on top of that. And so this system was developed by this trustworthy systems group, and it's a practical thing. You can actually put it on chips, and it's used on like there are mobile phones that use this kind of this kernel code in them, and so it's assured that if anything goes wrong, it goes wrong above the level of the very hardware of the system, I guess.
I guess that's not only good against mistakes, but against security threats as well.
Exactly. So I mean, that's the main reason you want to do this is because, I mean, so some of the big sort of show-stopping bugs in the past few years have been these really I mean, they're sort of extraordinarily clever attacks. So there's this thing called Spectre and Meltdown a few years ago. And so people got very, well, it was a really big problem, okay, for a few years, maybe less than a few years, but for a while. And the thing is, if you actually read about how the attack works, it's so clever and it's just extraordinarily clever. And unless you're someone who's just sitting there thinking, how can I possibly attack this processor? Then there's no way that anyone kind of thinking remotely sensibly would ever come up with that. And so that sort of explains the need to not just go, I can look at this and think it looks okay, but to try and actually go away and say, I want to check that under all circumstances, I can't possibly leak information, secure information from this system.
Yes, I can see that's very important. And as you say,
Yes.
it's widely used.
Yes, that's right. That's right. So it's now an open source kind of project, but it's still run quite, I mean, there's still a big group of people working on it in Australia.
And there's lots of other security issues like that, separate to the kernels in phones and computers, that might lend itself to that sort of approach of verification.
That's right. So I mean, it's a big thing. So there are various. So I mean, so maybe I should come clean, right? So we talked about game semantics.
Yes.
So and there's a sort of range of degrees to which you create this stuff with a hope that it's going to be used directly for kind of these practical purposes. Okay. So if I'm honest, game semantics is slightly further along towards the kind of we're doing this because it's fun, or maybe I mean, okay, that's not selling it correctly. Okay, so, or what? It's not even. I'm not even trying to sell it, but that's not the sort of thought process, right? So the thought process is this is actually quite a complicated thing, and it only looks simple because we haven't really understood it properly. And so what we should try and do is understand it properly. And when we do that, it turns out to be much more kind of delicate than at first we thought. And we come up with this game semantics, and that turns out to be kind of somehow, it's a bit of a head scratcher. It's not quite what you expect, but all that's doing is revealing the underlying complexity of what was there. Okay?
Yes.
So, so, and so you're doing this not for fun necessarily. I mean, it is quite fun, but you're doing it in order to understand what the real complexity of the situation is. Okay, and so that is maybe more on that kind of doing it for its own sake kind of application. So when it comes down to actual practical formal verification, there's another setting which is very commonly used, which actually again comes from mathematics and from things quite close to category theory that I do, which is something called type theory. Okay, so type theory, I guess, originates in sort of I guess it's about 100 years old now. So I guess a big thing in mathematical logic was, so 100 years ago, like Bertrand Russell and Whitehead were trying to create a foundation for mathematics that would work for everything and kind of explain everything that happened in mathematics. And so they wrote this famous book, which no one's really ever read, but this very long book, Principia Mathematica, which was supposed to be like a formal treatment of all of mathematics, just starting from the very least thing you could start with. And so it turned out that this was an impossible dream. So Kurt Gödel, the logician, showed that their dream could never be fulfilled, that if you tried to write down a foundation for all of mathematics, there'd always be something else that was more complicated than anything that your system could handle at the moment, which you'd have to add extra rules to describe. So, I mean, so that was an amazing, amazing kind of the most comprehensive refutation of anyone's program ever made, I think.
So that's
Um,
the incompleteness theorem?
the incompleteness theorem. So, yes, so that's Gödel's incompleteness theorems. And so, what has this got to do with type theory? Well, a direct result of this was that Bertrand Russell went away and said, okay, well, maybe we can't do this one foundation for all of mathematics, but maybe at least we can come up with something which will allow us to avoid these apparent paradoxes which had turned up within mathematics. And so he came up with something called type theory. So that's very different from what nowadays is called type theory, but that's the sort of the genesis of the idea was in this work of Bertrand Russell. And so the place it turned up again subsequently was basically in programming languages. So when we talk about types in programming languages, we mean things like, they're basically the sorts of stuff that your computer can work with. So it might be things like strings or integers or kind of lists of names or something like this. Okay, so a type is just like a collection of stuff, like a domain of sort of values that could be the inputs or outputs of a function. Okay, and so type theory is to do with studying that kind of structure from a mathematical perspective. So, I mean, I guess sort of modern type theory as you know it first started probably with work sort of around the kind of related to people around the time and sort of in that sort of same intellectual space as Alan Turing and things like that. But it really, I guess, took off due to work in Sweden in the 1970s. So Swedish mathematician philosopher called Per Martin Löf. And so he had this version of type theory. So the type theory can represent your programming languages, but his version of type theory could also, within the same system, reason about the programs. Okay, so you could prove that your program does what it's supposed to do in the same language as the program itself, basically, which is quite a remarkable thing to be able to do, really, I think.
Absolutely.
And so the point is that there are these very, very practical, concrete systems out there that are based on this this Martin Löf's type theory, which allow you to take a program and verify that it does exactly what it's supposed to do under all circumstances. So a lot of this comes from France. So there's a sort of tradition in French computer science of giving everything terrible names. And so an instance of this is one of the main systems for doing this formal verification, which is called COQ, C-O-Q. So this is named after, in part, well, after the bird, and in part after one of the leading people within type theory. He's called Thierry Coquon. So he's a French mathematician who lives and works in Sweden as part of this sort of community of type theorists in Sweden.
Fantastic. Well, yes, unfortunate. Good for French, but a little unfortunate in English. We have just over 4 minutes left before we're brutally cut off by Zoom. Would you like to make a concluding statement, or would you like me to get you another session?
Okay, so let's have a think. So I guess let's see, what can I say? So I guess the thing with maths is, as I've said before, I think it's kind of sorely misunderstood in many ways, right? So maths may appear to be about kind of calculation and very precise statements that are either right or wrong. And indeed, that is true. But really, it's actually about just studying ways of thinking and then trying to make precise statements about those ways of thinking. So if you like, it's a bit like law in some sense, right? So in law, um, you have something you'd like to say. You'd like to say, if you kill someone, that's a bad thing, and we'd like to make sure that kind of we discourage people from doing that in a suitable way. Okay, and so you make a law, and you want your law to be precise enough that it doesn't catch people who are not killing people, but also vague enough that people can't get off on technicalities. And maths is kind of like that. It's like you want to create structures that are precise enough you can make statements about them, but also broad enough that you can sort of let your intellect play over them and come up with new things starting from them. They don't just constrain you to what you already know. They let you build new things on top of that.
That's an excellent way to finish the interview. Richard, thank you so much.
Thank you. Thank you.
That was awesome. And you've got to time as well.
Fantastic. Oh, thanks very much. That was really fun.
That was
I hope
fun.
Study science, because you will find in the study of science a richer, more rewarding life.